Hello everyone. Today I want to talk about multiple linear regression. But at the beginning, I want to go through some of the statistical analysis, graph, and something that we haven't done before. Okay, so I'm going to use the data set, serial data set for this lecture. And as a review, we can see we have some variables. Some of them are numerical, some of them are categorical, and in the first row we have index column, which are the name of these serials. Okay, so I want to use a package that we used before, Seaborn. Import Seaborn as let's import it as SNS. I think we used this before. And then we are going to, actually we already imported plot. Let's bring it here as well if I'm going to use that. So what I'm going to do, I'm going to make a correlation data set, which is the subset of, actually, you know what, let's call this sub data set, because this data set is not going to contain the correlation. I'm just using this sub data set to to create a correlation matrix that you will see a lot in data analysis. Okay, so there are some variables that I want to include in this matrix. So this is a calorie, and then what else? Let's use protein, fat. What else? Let's use where is carb, and let's use sugar. And what else? Is this enough? Oh, rating. Last time we saw rating had kind of different group of rating that we created had effect on calories. Okay, so I'm creating a sub data set like this of 1, 2, 3, 4, 5 columns of sub data set of 5 columns of the data set. Okay, so what I'm going to do, I'm going to use SNS dot pair plot. I think that will help us to do what we want to, what I want to show. Let's see. If not, I'm going to use matplotlib. Let's see what happens. Okay, good. So I created a correlation matrix. In this correlation matrix, I wish it was smaller. We have calorie, fat, carb, sugar, rating, all of them versus the other variable. As you see on row and columns, we have the same variables. What happens? We are drawing a scatter plot of calories on x-axis, for example, versus rating. And then this scatter plot says x-axis contains calorie, and then y-axis shows sugar. Again, x-axis shows calorie. So as long as I am in a first column, means all the x-axis in first column shows the calorie, and the y-axis shows, for example, fat. And this one, look, will be the calorie versus calorie, which shows a kind of histogram of calorie. Okay, so what we have here, I'm going to remove fat to have a smaller matrix so you can see everything better, hopefully. Yes, here it is. Okay, so what happens, let's see. Calorie versus rating. So maybe we have a kind of linear relation, maybe not, maybe it's a curvature. But if we had more data, it would be much easier to assume if this is a linear or curvature relationship. But fitting the model will show us if the linear model fit the best or the curvature model fit the best. We will talk about that later. So here we see, for example, the rating which has the highest rating, which is kind of here, has the lowest calorie, and we see most majority of rating below 60 something will have the calorie between let's say 90 to 125 or 125. Yes, so it's a kind of good visualization tool that can help us to understand how some of variables are associated. So for example, this one you will see the calories for all the sugars, all the cereals are mostly between 75 to 100, like let's say 25, but there are couple of this cereal that has a higher calorie based on sugar, and then lower calorie based on the sugar. So sugar 0 shows the calorie 0. Calorie, actually sugar 0, calorie 50. Okay, and then the highest calorie will belong to the cereal which has the sugar 12.5, right? And then what about this one, carb? So the 0 calorie actually cereal can have carb between, like let's say 8 or 7 to 40, right? And the majority of different carb shows the calorie between 75 to like 150, right? And then the calorie is kind of normally distributed between all the cereal. Then what happens here, for example, rating. The rating is right skewed, the histogram of rating. So what this means the majority of cereal in our data set has a rating below 40, right? Or what was the average of rating? The majority are below a certain point, like let's say center or mean of rating. What else? So here also, let's say again rating versus calorie, we see a kind of negative slope, means as a rating increases, the calorie will decrease, right? So what is the negative slope means one variable increases, another will decrease. Am I right? So for rating high, the calorie are smaller. For rating low, the calorie is on y-axis is calorie is higher, right? So in this way you can explain it. So what about this one? Wow, this one is the same. Like I see a kind of negative slope for this kind of data set, rating versus calorie. Here also I will see a negative slope for rating versus sugar. So as sugar increases, as rating increases on x-axis, the sugar will decrease on y-axis. And as rating decreases on x-axis, the the sugar is increasing on y-axis. So there is a negative trend here, also negative trend. So we see that rating versus sugar, rating versus calorie are the kind of negatively associated. Okay, so what about carbs? So I cannot see any specific trend. Maybe even there isn't any correlation between rating and carb. So now participation point for you. You should find out the correlation between carb and rating, and correlation between, actually, you know what? Calculate correlation between rating and all the other variables which are numerical. Okay, so calculate the correlation between all the rating versus all the other variables that are numerical. Okay, so here also, if this was a right skewed for rating, this one is sort of, well, I cannot say left skewed, but it seems left skewed. Maybe if we had more data set, we could see that more obviously. But what is this? This is carb. Carb doesn't show any specific pattern to the other variables. Maybe this one a little bit and this one. So when we are talking about clustering, we can easily or more, kind of freely talk about the correlation, or we separate data set, each variable to the cluster they have, and then we will specifically talk about each cluster that is created. Okay, so this is the correlation matrix that I wanted to show you. So what I'm going to do, I'm going to choose rating and what else? Sugar and calories. What else? Let's try fat instead of carb. See what happens, what we have. So where's fat? So fat is kind of showing, because the data seems categorical and rating, so that's why we see this kind of pattern. It's like a line. So for this reason, it's possible that this is because, it's obviously shows a categorical pattern because this is a rating, or kind of, do you remember we talked about ordering? So this is kind of that data set. So that's why. Okay, so let's bring the carb back, and I'm going to create independent variables. A data set. Oh, actually, before that, I really like to talk about some kind of manipulation in data set. Let's say in a data set, we have a type. Okay, so I'm going to talk about type. So let's say I want to manipulate this data set. I don't want to have C or H in my in this data set for the variable type. So how can I change that? Do you remember we talked about coding for categorical variable? So here I'm going to change something in my data set. I'm going to add a new column, which is I'm going to call it new type. So I'm creating a new column named new type, and then I'm going to say from the data set, the type column replace what? Replace, let's see, replace, I'm going to create a curly bracket inside the parentheses, and I'm going to say 0 for C, all the cereal that are cold, and 1 for all the cereal that are hot. So do you remember we had C and H? C and H are previous names for hot and cold. 0 and 1, what happened? 0 and 1 are becoming the new name in parentheses coding. So let's see if I do this, what we see in the data set. Okay, so now I have a new column. Instead of, oh, what did I do? Instead of C, I should have 0 instead of, what is that? Instead of hot, I'm going to have 1. What we are going to do, so C becomes 0 and H becomes 1. Now this should be correct. Yeah, okay, so for all the cereal that were cold, now we have 0 in the new column. So we didn't replace the previous column type by the new one. We just created a new column and we named it new type. And then now in this new column, we have 0 and 1 instead of cold and hot. So this is the way you can create a new column and change the variable's name. For example, rating, do you remember I have chosen, what is that? Above the mean of rating as high rating and below the mean of rating as low rating. So you can try that too. Maybe this should be a participation point. So add another column, call that new rating, and then replace all the rating that are above the mean of rating by write down by high rate, for example, and then whatever is below rating, below the mean rating, you can write down low rate. So high rate for all the rating that are above the mean rating. So first you have to calculate the mean of rating, and then you should specify for all the rating that are above mean, assign high rate, and then for all the mean which is below the mean of rating, assign low rate. And then in a new column you will have high rate, low rate instead of all these numbers. Okay, that will be your second participation point for this lecture. Okay, so now I want to create X variables. A data frame of X variables. Let's call them independence and dataset .loc, and okay, so I'm going to choose calorie, carb, rating, all of these, and I'm going to now talk about multiple linear regression. Okay, so I'm going to, oh, actually, I'm not choosing this as my independent. So my independent will be carb, sugar, rating, right? And then my dependent variable, I want to say dependent variable is calorie. So I want to see what's the effect of those independent variable on this dependent variable. Okay, so what we are going to get, let's get some information, like let's print the independent dot shape gives us 77 individuals, and we have 3 variables, as you know, and I'm going to create my model SKLM. Am I right? Here. So I'm going to use import sklearn linear model, and the brief name is SKLM. And I'm going to get the linear regression from this package, and I'm going to feed the model, and the model will be based on X and the calories. Am I right? Okay, good. And then so feed means we're already feeding the model. So what I'm doing, I created an instance of linear regression model, then I feed this model using the data. First, actually I want to write this down here. First argument is X variables, and then the second argument, as you know, is the Y variable. Okay, so what I'm going to do, I'm going to print the coefficient of determination. What is that? R squared, right? R squared. And then what is the method for that? We use score, and we are going to use this too. What did I do? Oh, the model is capital M. Good. So the coefficient of determination is 60. Not bad. 60% of variation of Y means calorie on the independent variables is explained by the model. Then I'm going to print intercepts, and what else? We are going to use model dot intercept. I don't know why they are adding this kind of underscore for their method. So well, what I found about Python, it's not as neat as the especially analyzing the data with Python is not as neat as and beautiful as R, for example. So obviously R is the statistical software. It's specifically for statistical purposes. But well, Python is more popular in between all the different kind of field, computer science, all different kind of field. But a statistical software like R is specifically for statistic people and not popular among other people in other field of a study. So, okay, so we are going to find a slope. Model dot coefficients, well, COEF. Okay, so let's see. What did I write again? Really? Okay, good. So now what this says if we have a linear line based on all the three variables we chose, so our line will be something like this: y equal to x1 plus x2 plus x3 plus the error in the model, and we will have intercept, we will have a slope for each of them, b2, b3. Okay, so it will be something similar to this, right? We have a slope, we have intercept, a slope for x1, a slope for x2, a slope for x3, and this is the coefficient, means 1.79 for b1, 1.59 for b2, negative 0.60 for b3. Okay, so let me write this down based on our study. So calories is y, carb is x1, so I'm going to multiply to carb, and then sugar is x2, multiply to sugar, x3 is rating. Now you see what's going on. Especially rating was so easy to understand. So it says the slope between rating and calorie is negative, means as rating increases, the amount of calorie decreases. And this one says as sugar increases, calorie increases. As carb increases, the calorie will increases. Okay, so this is the way we explain it, right? What was the slope now? Let's see. Oh, actually intercept 95.35 means with all these variables being zero, if you start with the initial model with all these variables equals 0, we will remain with intercept, which is 95. Means our model will start on y-axis at 95, at 0.95 as calorie, and if the rest of variables are equal 0. Okay. So there is another way to get all of this. What is that other way? Let me write it down here. The other method. So what is the other method? OLS, ordinary linear regression. We are going to use model formula. Where is that? This one. We are going to use this. Using, well, if I put this here, you will remember it. And then what we used for this one, linear regression is, okay, I'm going to use this, bring it here and say using this one. And then I'm going to cut this one and create a box here. So you know, from here we are talking about multiple regression, and then this is the method I used for the first one, and this is going to be the next model. So okay, I'm going to create the model. You can always change the model name, write down model 2. Okay, OLS actually, when I was reading about this in Python, it used to be capital OLS. So if you're looking up this, you can see the difference. I mean, you may find this somewhere. Okay, so in OLS, we don't need to create a model like, we don't need to create independent variables the way I did here. So what we do, I'm going to show you now. I'm going to add all these on the right side of tilde. We talked about this before, I'm sure we talked about this. And then calorie is the y. Okay, so let me write this down here. Y tilde x1 plus x2 plus x3 plus dot dot dot. Now you understand. Okay, so what I need for this one, well, I need to mention my data set, right? Without the data set, how it will be clear that I'm getting these variables from what data set. Okay, so I'm going to do this. If I run this, I have a model that I haven't fit yet. But if I write down dot fit with parentheses, I'm going to fit the model. Like here, we use dot fit, but inside this fit, we have to write down x and y. So because this method is totally different from this method I'm using. So that's the reason. Okay, so we fit the model. We create the model and fit the model at the same time, right? So now what I'm going to get, I'm going to print model dot summary. Do I need parentheses? I think I need, because I have multiple information in this. Okay, here it is. Well, you know what, I'm curious. I want to see what happens if I don't use print. I didn't try this yet. That's nice. Okay, so this reminds me of R. So if I don't use print, the kind of pattern for this table will be different. Okay, so now let's go through this table, what it says. So the main information is here. First of all, so let me compare what result we got here from the previous method. 0.60 was R squared, coefficient of determination, and here is exact same, right? And then intercept 95, here we have 95 intercept, right? And then 1.79, 1.59, and negative 0.60. So these are identical, right? So it doesn't matter which method you are using, as long as you have the similar model, you will have the similar result. Okay, so let's go through this result and see what's going on. So we have carb, we have sugar, we have rating. The dependent variable shows calorie, right? The model we are using OLS. The method we are using least squares. and date actually 3 days after New Year 2021. And then time, and then number of observation, we have 77 observations, and the residual will be, so let's go through all of this and explain what is residual. So degree of freedom for residual is the degree of freedom of what's that, the number of observation, actually 77, minus the number of parameters we have in this study. So we have 3 explanatory variable, 1 dependent variable, 4 variables. So 77 minus 4 is 73, correct? And then degree of freedom for the model is the number of explanatory variables we have in the model. So it's not including the constant. Okay, so R squared, where's R squared? Here. R squared, you already know what is that. It's a statistical measure and explains the variability of the dependent variable on the explanatory variables based on the model. So the regression line, it says how well the regression line approximates the real data points. Then we have adjusted R square. So what is adjusted R square? Adjusted R square is helping us to compare models. So it's based on different samples that is taken over and over from the model, and it calculates the R square based on that. So this is the above value adjusted based on the number of observations and also degree of freedom of residual. So you can study this further. Whenever we want to compare 2-3 different models, we look at the improvement of adjusted R square. That will help us to explain which model is improving and which model is getting worse. Okay, F statistic and T statistic, these are all the measures, statistical tests we are using, like the Z test statistic, T test statistic, and F test statistic. These are all the measure how significant the fit is. Means the mean squared error of the model. If you want to look at the F statistic formula, is the mean square error of the model divided by the mean square error of the residual. So this test statistic shows how well the model is significant. So the T test statistic, do we have it here? The T. So what T says for each of these variables, it says how statistically significant each of these coefficients are. So how statistically significant each of the coefficients are. So if we have a larger T, means we have a lower p-value. If we have a lower p-value, means the coefficients are statistically significant. Rating has a statistically significant coefficient with calorie. Sugar also, but not as significant as rating. Carb is very significant, but all of these we should pay attention to lots of other factors like R square, all of this, to see if this model is really a good model or not, if this statistically significant is based on overfitting or underfitting. We should consider all of these. And then what else we can talk about? Let's see. Probability. Look at this. So, actually there is a probability here. So what this says, whatever you see here, f statistic and probability, this will examine the whole model. It's not examining each single variable. So overall says, yeah, this model is a statistically significant model and all the variables are explaining the calorie very well because the p-value is very small. Do you remember small p-value means we are rejecting the null hypothesis and there is a effect of explanatory variables on the response variables. What else? Okay, a standard error. Do I see it in here or? Okay, I don't have it here. Assume that the covariance matrix of error correctly specified. Where is that? Okay, I don't see it now. We'll talk about that later. Okay, so what else we have? P-value. Let's talk about each of these single p-value. Okay, this one, for example. We talked about this based on after I talked about t. So when the we talk about p-value. P-value is the probability, right? And this probability says how well we can say the null hypothesis is being rejected or null hypothesis is not being rejected. And the null hypothesis in this case for each of them is that coefficient of, for example, sugar is equals 0, coefficient of carb is equals 0, coefficient of rating equals 0. So if I reject the null hypothesis, what that means the coefficient of rating on the model on the calorie is not 0. The coefficient of sugar is not 0. So the null hypothesis for probability for the for each of these says coefficient is equal 0. So what happens if I reject? If p-value is small, we reject the null, means the coefficient of that specific explanatory variable on the response variable is not 0. So when I reject the null hypothesis, means I'm rejecting this one. When I'm rejecting this one, means the coefficient of that explanatory variable on y is not 0. If I cannot reject the null hypothesis, means the coefficient is 0. So when that happens, when p-value is large. So when p-value is large, we cannot reject the null hypothesis, means the coefficient of this specific explanatory variable on the response is 0. So when p-value is small, we say the result is statistically significant, right? And then if p-value is large, the result is not statistically significant. So this is the situation that happens. Okay, so the next one we have, let's talk about the skewness. So this one says it is a measure of the symmetry of the data about the mean. And so normally distributed errors should be symmetrically distributed about the mean. So we also actually still didn't talk about the normality of residual yet. We should talk about that later. Okay, so yeah, this is about the skewness. And what else? So let's more talk about adjusted R-square. So let's say I was not satisfied of this model and I was thinking there's something wrong. If I wanted to add or subtract some of these variables, or I thought, okay, maybe carb has a curvature effect on the calorie and maybe this should be polynomial with like kind of power of 2, or this needs to be 1 like reciprocal of sugar. So all of this can happen, right? We can try and fit different model, compare these models. So there are something like adjusted R-square, AIC, BIC, log likelihood. These are all, everything can help us to detect the best model. If we are creating 2-3 different models and fitting 2-3 different models, we can compare them. Okay, so what our adjusted R-square is, it's kind of modified version of R-square and has been kind of adjusted for the number of predictors. How many predictors we had here? For example, we had 3 predictors here, right, in the model. And then the adjusted R-square increases only if the new term that we are adding to the model improves the model, and the model is kind of more than would be expected by chance. So the new term improves the model more than what we expected, what we expected that happened by chance. And it decreases when a predictor improves the model by less than the expected by chance, less than whatever we expected to happen by chance. And then AIC, BIC, these 2 measures are very famous. These are the fit criteria. These 2 both are kind of penalized likelihood, and there is a kind of formula for that. But both of them doing the similar things, talking about AIC and BIC is just based on your goals and your assumptions in the analysis, whatever assumption you have. AIC, for example, is the estimate of a constant plus the relative distance between the unknown true likelihood function of the data and the fitted likelihood function of the model. A lower AIC means a model is considered to be closer to reality. So if AIC is smaller, the model is better if you're comparing 2-3 different models. So what is BIC? BIC is the estimate of a function of the posterior probability of a model being true, and it's under kind of Bayesian setup. So that says a lower BIC means the model is considered to be more likely to be a true model. And BIC is similar to AIC but has a kind of higher penalty for models with more parameters or complex parameters. So the AIC tries to select a model that most adequately describe an unknown high kind of dimensional reality, and this means that kind of reality is never in the set of candidate models that are being considered. So on the kind of other hand, BIC tries to find a true model among the set of candidates. So maybe if you rely on BIC, it is much better, but you always can compare both of them when you are talking about model comparison. You can use both of them, not relying just one of them. So the lower BIC AIC in model comparison is much better. So imagine if you have model 1 is this one, and let's even create the second model, and let's say the second model doesn't have carb in there, right? And then so this is the second model. So look, AIC increased, BIC increased, right? In compared to AIC, BIC we had here 611, 621. So what this means, well, we didn't improve the model, we ruined the model. Look at R square. R square is 48 almost, but R square here was 60. So if I had carb in the model, it was much better explanation of model in compared to when now I don't have it, right? And the adjusted R square, look, it destroyed kind of, like in compared to this one was much better. So yeah, this is kind of comparison you can have between models to see which model is more adequate, more better, right? And then look, on the other hand, what happens when I removed carb. Now the effect of rating, influence of rating, the coefficient of rating on calorie increased in compared to the previous one. This one was negative 0.60 and now negative 0.80. Now in this model, more responsibility on rating in compared to the previous model. Now what happens to sugar? 0.40. So now sugar has less coefficient on the calorie. And well, look at this. Now sugar is not significant anymore on the calorie, but with having carb in the model, sugar had a significant effect on the model, right? So now let's do one thing. Let's keep the carb, remove the sugar, see what happens. Well, what I am doing, this is second model, and now I want to create a third model. Now in the third model, I kept the carb. Well, R square not good. Adjusted R square is not good. AIC, BIC, well, not as good as the first model, but better than the second model, right? The second model actually is almost similar to the third model, right? Am I missing anything or no? Actually, I'm missing something. Yeah. So the second model has 630. This model has lower AIC. So the third model is much better than the second model, right? And then let's look at the rating. Rating, well, increased. And then carb, not bad. Both of them are still significant. But when we remove the effect of carb from model, sugar will not be that significant. So you can compare all of these models and see how they are explaining the effect of explanatory variables on the model. Okay, I hope everything was kind of interesting and you understood something from this lecture. Let me know if you have any question, and we'll see you later.